For supervised classification, we have a variety of measures to evaluate how good our model is, because we have a reference point and then we can check what we got with the reference and come up with accuracy, precision, or recall. So, but cluster validity for unsupervised clustering is a bit challenging, and it can be also left to the person who actually did the clustering. Therefore, we call this eye of the beholder. Why do we need to evaluate them? Why do we need to know what the validity of a cluster? Because we would like to avoid finding patterns in noise. We want to maybe compare clustering algorithms, or we want to maybe compare the output clusters in cases where to tell if one cluster is better than the other one. So cluster validity is also an important topic after the clustering, just to make sure that we have a good enough cluster result. So if you look at random data and force it to a k-means, for instance, you can still find clusters within this data. And in this case, in this example, we have 3 clusters. We set k to 3, and then we got a set of points. Those are being clustered. But in reality, we know that these are just random points. There's nothing in it. It shouldn't be a good clustering, but k-means will still find us clusters, just like db scan or complete link in the k-means. So this is something we would like to avoid at the end, if possible. So when we have cluster validation, we need to understand the clustering tendency of a set of data. We may want to determine that, so that we can tell that non-random structures exist in the data. We may want to compare the results of a cluster analysis to an externally known class labels. So this is the case if it is supervised. We have some indication about or some sense of the data that sounds good, and compare the output as maybe expectations. If we only use the data without external reference, then we can actually look at the fit and tell that if this is a good fit of cluster analysis. And if we have different sets of clusters, we want to maybe tell which one is better. And we also don't know how many clusters we need, so we come up with a number of clusters, and just to make sure that that correct number of clusters is actually specified. So these are different aspects of cluster validation. So how do you measure cluster validity? We have numerical measures judge various aspects of cluster validity. So we can in general put in 3 types: external index, internal index, and relative index. In the external index, we are more or less doing a supervised check against some class labels, some data reference points we have. If we have internal index, we don't have any external reference. We just use the existing error in the fit and then decide if this is a sufficiently good enough cluster. Or if we don't have any, if we are not quite interested in external or internal index, we just want to know if one cluster is any different than other cluster, then we can actually just calculate an index relative to each other and decide if one is any better than other, for instance, using SSE or entropy. We may be using cluster correlation between proximity matrix and incidence matrix. So for a cluster, we can obtain a proximity matrix between points, and we also come up with similarity matrix. So in each column and row we have points sorted, or it's just it doesn't need to be sorted, but it's actually placed. And what we will be doing is when we obtain proximity matrix and similarity matrix, we can actually look if they are overlapping. If there is a relationship, if they belong to the same cluster, then we call either in the proximity matrix or in the similarity matrix 1. If somehow point X, for instance, doesn't have the same cluster with point Y, then that entry will be, that cell in the matrix will be 0. If they are in the same, let's say point X and point Y belongs to the same cluster, then we call it 1. And once we obtain that distance matrix and similarity matrix, then we can look how close those are. And using correlation coefficient, which is a symmetric matrix at the end and has only half the entries needed to be calculated, basically if it is close to 1 in absolute value, then we can tell that these are highly correlated. But if they are not somehow, then it is actually not uncorrelated or not correlated. But for some density and continuity based clusters, this may not be a good measure, so you need to be aware about that. So let's look at this example here. We have a cluster. We have X and Y in 2 dimensions, and we have these 3 clusters. Using k-means, we actually identify those. Now, I will obtain a similarity matrix and proximity matrix for each of these. This is a proper cluster, and this is just a random number clustering. So I will calculate similarity and proximity matrix for the first one and look if they are correlated or not. So in this case, because this is a good cluster, it should have a high correlation. Although it is a negatively correlated, this is still highly correlated, close to being 1. And in the case of a random number, it is not correlated at all, because it's a number far from 1. So this is how you can actually tell that this is maybe a proper clustering, but this is not. You can also visually inspect and tell if a cluster is good or not by looking at similarity matrix. So we have points, we got 100 points here. So we are going to put 100 points and 100 points. So this is a matrix I will form. It's an n by n matrix. N is the number of points. So 0 to 100, and again 0 to 100 points here. And if, let's say, point 10 has some similarity with point 20, so you take point from X and you take point from Y, and you call that, based on similarity number, you call that, if it is completely similar, like if it is itself, that's going to be 1 definitely, but if it's not itself, it will be a number that's close. Then you may mark as in heat map a dark color, for instance. And when you sort these with class labels, when you group them, so at the end you will see 3 clusters with sharp images. More or less, I can call this a sharp image. But in the case of a random number, random data, there is really not a cluster, so I will be actually sorting. So this is maybe my largest cluster. So it is points between 0 and 60, and maybe 0 and 60. So this is that blue region, likely this is the case. And if I look at this, I would actually tell you that a number here is not quite correlated with a number there, although they are marked maybe the same color, blue. There's a bit, not much similarity. So some are red because they are maybe close by accident, but overall there isn't not much of a crisp image here. And this is using DB scan, but it doesn't matter. You can still use k-means. You can use complete link. Again, there is not much of a correlation due to crisp image not being shown. So if we have again a density based clustering method and we use this in this data set, dbScan works well for this type of problem. And if you look at similarity matrix that's formed, and these are again sorted by label. So for instance, I'm not sure, but maybe the red ones are in this column, like between 0 and maybe 700, again 0 and 700. So there's really high correlation here, there's high correlation here. So there's you can clearly see that there's a pattern here. But there's again some areas that's a bit gray, not quite correlated, but I can clearly see some really sharp sets. So visually you can inspect the validity of cluster and tell that okay, this is maybe sufficiently good enough for the purpose. If you look at internal measures, we can be using SSE, sum of squared errors. Clusters in more complicated figures aren't well separated. We can then use SSE, like for internal index, and measure the goodness of a clustering structure without external information or reference. So note that SSE is good for comparing two clusterings or two clusters, either algorithms or the clusters themselves. You can actually use SSE to evaluate the goodness, and also be used to find the number of clusters. If you are interested in finding out how many is going to be the best number for clusters count, then you may actually use SSE, where you actually plot number of cluster k versus SSE, and when you see a sharp drop at the beginning, and it will actually slow down at some moment because due to overfitting it won't help anymore. So you increase more k, it doesn't reduce the SSE anymore, so it becomes more or less flat. So this is the elbow point where you can actually tell that the 10 is maybe the good number for this data set to be used when you are estimating the count for cluster. In a more complicated data set, this will still be sufficient. Again, these are errors, and these are the k, different k, and you can clearly see that it's about 7, 8, it's breaking, and then on it's not changing as much. Definitely the more you increase k, the less error you will have, but the drop will be much less significant. So you may actually stop that, okay, maybe I will settle with 7 and let the system find 7 clusters for you using k-means or some other algorithm. So what we need is a framework for cluster validity, because for instance, if we measure that we got 10 as an index number, for instance, how do you know if this is good, fair, or poor? So with that, a framework to interpret any measure. We can get help from statistics, and in that case we can see how atypical a clustering result will be. For instance, if we have an index value, it is unlikely, then the cluster results are valid. I'll explain that with example in the coming slides. We can compare the values of an index that results from random data or clusterings to those of a clustering result. Basically, you have random and you get some index and compare your number with that random data cluster and tell that okay, this is maybe significantly different than random and maybe a valid cluster. Sorry, I will actually show you. So when comparing the results of two different sets of cluster analysis, a framework is less necessary because we are just looking at numbers. Those are relative numbers. So it may not be that critical to know what that number really is, as long as those are relatively comparisons. We may be just okay with that. So using squared sum errors, so we have this data set on the left bottom. These are proper tree clusters with using k-means, and if you actually calculate the SSE for this set, and basically looking at midpoints, these are proper tree clusters, you will actually get a SSE of 0.005, or in that range basically. But if you actually just use the same range and just produce random data, that means we don't have a really clustered situation, it is just all over the place, then we can actually obtain, and if you do this 500 times, if you just produce random numbers and get SSE, if you produce random numbers and get SSE, you will obtain a histogram like this. And in that case, using just random numbers, you are looking around 0.02 or 0.0225 or something like that. So somewhere around here, it is actually having a mean. On the other hand, my standard error was 0.005, which is maybe down here. So that happening by chance is unlikely. In that case, if I see a clustering error such low, then I can probably assume that this is a proper clustering. So basically, I'm comparing with some random generated clusters data set, and I fit clusters to that, and I can actually compare the results, and I see not much of a change, because it's going to be somewhere really high with respect to a proper clustering. So I can actually easily say that this is a good cluster. We already talked about correlation and similarity and proximity matrices of k-means clustering for two data sets. We have correlation coefficient being 0.92 for this data set, and correlation for random is 0.58. Between similarity and proximity, there's really not much correlation in this case, but there's a correlation here, and I can actually, assuming this number is good, then I can tell you that this is a proper clustering. In the random case, I wouldn't have any random any good clustering if it was just random. So it must be some significant difference that is important. These are more or less cluster cohesions. We actually check how closely objects are within a cluster. That's cohesion. We also are interested in separation, like how distinct or well separated a cluster from another cluster. So we do have really two aspects of cluster validity. We have how well we are clustered within a cluster and how well we are separated from others. And for that, you can come up with these two numbers. So C is cluster here, cluster. So we have a set of clusters, and for each cluster, I will actually calculate SSE and sum them up. So this is my middle point or mean. Any point in that cluster, I will actually compare the distance, add them up, and obtain a within sum squares. I also can calculate between cluster sum of squares, BSS. For all the clusters, I have middle points, and I actually check how these are actually separated from each other. So CI is the size of the cluster here. So I will tell you I will give you an example here. So using these internal measures, BSS plus WSS, which should be a constant, using only SSE. So here, if we have SSE for k equals 1, single cluster, you got to see this data, and mean is 3. You can easily identify that, determine that. So SSE is 1 minus 3, 2 minus 3, 4 minus 3, 5 minus 4, and for each of these I will take the square of it, and I will come up with a number 10. And because I have only single cluster, so there is really nothing to, I will actually compare my cluster with any other cluster. So that's 4 times 3 minus 3, that's the same point, that's the origin. Then I will have BSS 0. So if you add these two, 10 plus 0 is 10. That's a number that I'm looking now, that's a constant. So if I actually come up with 2 clusters, so this was 1 cluster and my 2 clusters, then I will have M1 and M2, and that's the overall M. So if you calculate 1 minus 1.5, 2 minus 1.5, and you will take the square of these, plus 4 minus M2 and 5 minus M2 and square of these, and you will come up with SSE1. Because it has to be 10, if you sum them up, then the rest should be 9. That is between cluster separation. And you can actually verify that. So you have 2, that's the size of the cluster, times M1 minus 3, which is M, right? So that is 1.3 minus 1.5, and you get the square of it. And when you do the math, and you will actually calculate that to be 9. So we can use those measures. So you really look for, okay, within one distance I can actually have a centroid, and in between those two clusters I have a 9. And if you sort of look at the ratio, this is really high, and I can maybe assume that these are well separated and closely bundled clusters, and that may actually be a good thing. So here you can visually see there's cohesion and there's separation. A proximity graph based approach can also be used for cohesion and separation. Cluster cohesion is the sum of the weight of all links within a cluster, if it is like a proximity graph, and then cluster separation is you take a point and then compare each point with other points in other clusters, and you do that for all points in that cluster, and calculate separation and cohesion for by actually doing quite a bit calculation. We can combine these cohesion and separation into a silhouette coefficient, but for individual points as well as clustering and clusters and clusterings. So if we take an individual point I, for instance, as you see in this picture here, we have I. For this point I will calculate the average distance to the points in its cluster. So how many points I do have in this cluster, I don't know, but I will calculate and take the average distance. Then I will also take this point, and for a cluster, because I might have multiple clusters, so let's say this is one cluster, one of the clusters outside me, it's not me but another cluster, I will calculate how far this is to the other clusters points, so sum them up and you take the average. And you do this for third one and fourth one and fifth one, and you take the minimum at the end and use as B. And silhouette coefficient is then given by B minus A divided by maximum of AB. Whichever is maximum, you can use that. And that should give you typically a number between 0 and 1. And the closer to 1, the better it is. So we want that to be a good indicator, using both cohesion and separation as an internal measure. We can also have external measures for cluster validity, like entropy and purity. Here I have a LA document set. This is from newspaper articles, and I decided that I will use 6 clusters, and I come up with titles being entertainment, financial, foreign, metro, national, and sports. So these are topics, and these are the clusters that I came up with. And now this is sort of checking how well I did. If it's similar to like a confusion matrix almost, but not quite that. So I'm hoping that in each cluster I will have only a topic, but obviously that's not going to be perfect. So let's say I have decided that I have a cluster 1, and most of those in 1 belong to metro. This is supervised, that I know it's a metro article, type article, and we have some national and some sports, a little bit foreign and very little entertainment and financial. So I know that that article belongs to more likely a metro. And as you can see, we have a high number here, and you can actually calculate entropy for this set only, like right there. So you can use this formula right here, Pij, how many do I have plus the log of that, and then you sum them up and you will come up with an entropy being 1.2, and purity is sort of reverse of that, how pure that is, 0.74. It's not that bad. It is heavily metro. It is still really good in that sense, but there's again others. You want it to be ideally more pure, like here in third cluster we have 671 of them is in sports category, and there's a few others, and this is really pure, 0.97, so that's close to 1. And entropy is also very low, so when purity is high, close to 1, then you will have a low entropy likely, which is a lower entropy, the better it is a better cluster. So you can also use some external data after the clustering. This is in a way supervised, and just to make sure that okay, I didn't do maybe too bad with this algorithm. But except in fourth cluster, for instance, the purity is really low, so it is almost equally distributed, except sports is 2 here, but these are more or less well, foreign is not as also equal, but you can understand the point that you can't quite distinguish between financial and metro here, or national, because the numbers are really high for those. So it could have been a mixture of all of that. So the validation of a clustering structure is the most difficult and frustrating part of the cluster analysis, because there's always a better cluster. Without a strong effort in this direction, cluster analysis will remain a black art accessible only to those true believers who have experience and great courage. Again, it requires some expertise, some sense of data to actually take on that. So this is by Janes and Dubs. And this is enough for cluster validity, and see you in another lecture.